Okay, we're doing it. It is review day. So I'm hoping that people have some questions for me or some topics that they want me to go over. Has to do with an exam, so it has to be blue. People feel blue when they think about exams. We'll see if we can show them that, but be more excited.
Can you go over grammar to NPDA?
Grammar to NPDA.
I know there was a trick where it's like the left side is the state,
Yeah,
the right side.
yeah.
Yeah, I think that's Greibach number 4.
It is. It does have to be in GNF.
Oh,
So let's say, I'm even gonna say GNF to NPDA.
That's the easiest way to do it.
Because, yeah, if it's in GNF, there is an algorithm to do it. So you would either need to convert anything in some kind of context-free grammar. You would want to do this conversion first, but I will not make you do some kind of, we didn't talk about GNF or how to convert into GNF. So if this were to show up on an exam, you would start from this point. But in general, you want to make sure that you convert it to GNF because it is so much easier. So first and foremost, who can tell me the form of Greibach form?
2 terminals, 2 non-terminals.
That would be, that's Chomsky norm.
Isn't it one terminal followed by a non-terminal because you're parsing left to right always?
So yeah, it's a single terminal followed by any number of non-terminals. So we could have something like S-A-A. Why not? Now, A will go to single terminal. Something like that. That's gonna loop on itself. Yeah. We need. There we go. That fixes everything. Just make a single production with nothing but terminals, fixes everything. So if we're making this NPDA, anyone want to walk me through what are the rules of construction? How do we do it?
It starts off with an A.
So we know that if we're making an NPDA for this, we're going to have some kind of initial state. And the purpose of this initial state is to get the start non-terminal on the stack. So we're not going to read anything from the input. So first is lambda. What are we popping? There's currently nothing on the stack, so there's nothing to pop. And we're going to push the start non-terminal. Whenever we deal with this start non-terminal as the left-hand side, we're going to push it again on the right-hand side after we pop it to make sure that we need to evaluate it to be able to do this. So in Q1, this is going to be everything that we can get to from any of these productions, really. We just need to know what is on top of the stack. So the stack is going to contain the non-terminals in this grammar, and we read the symbols that are the terminals. The reason we can only have one of these is because we can only transition on a single character in the string. So the form of this having a single terminal at the front of it means that that defines the symbol that we are going to make. So let's start with just this. This would say we're going to loop from Q1 to itself. What symbol do we read? The B. So we're going to, on a B, we want to pop, in this case, the S. And if we just push nothing, that would say that this can go directly to a B and now have an empty stack. So we want to be able to do that. If we put on the S back, this would say that there's still something to evaluate. So you only want to do that if there are other things. So we're not going to do that. This would be the transition for that. Any questions on this transition referring to just this production?
Oh,
Would that mean Q1 has to be a final though? Or could we just?
So
say that
yeah,
there's
we're
no-
going to eventually be able to, as long as the stack is empty, not even having an S on it, we can transition over to an accepting state. That will be our Q2. So read nothing, pop nothing, push nothing, go over there. And now we can only accept if we're at the end of the string. So if the entire string is just B, we would, in the stack, push on the S, pop the S, read the B, and on an empty stack, move over to Q2 and accept.
That implies you can accept the ending string, right? Or no, you can't.
Yeah.
So you have the S production. So
Yes,
you
we have to remove the S in some capacity. Yeah, this isn't quite the same as the bottom of stack character that we've had before that I've said is okay to leave on. In this, you have to leave it off. Have to get rid of it because that bottom of stack symbol refers to the start non-terminal in the grammar. What's the next production? Let's handle this production.
CNAs.
So we could CNA, yep, that's the character we're gonna read from the input. What do we pop?
S,
The left-hand side here, the S. What do we push?
AA, or
SAA.
You have to put another S on the end of that.
We do not, because we are replacing this S with these. So we're going to say this S becomes these. What's next? Which one do we want to handle next?
could be something like A lambda.
Yeah, for this one.
Which would also handle B's production just to A as well.
Yeah, well, it's gonna be slightly different because we pop something that is slightly different. So we will still need two transitions for this, but you are right that we're gonna have two. One that says on an A, we want to pop a capital A and we want to push nothing. So this just gets rid of the A and moves past this A in the input string. If we wanted to do this one as well, since it's very similar in form to this, we would just say on an A, we can pop a B and push nothing. One left. What is its form? Yeah, we're gonna read a B. We're going to pop the left-hand side, which is an A. We're going to push the right-hand side non-terminals, an AB. Let's run through this with an example, just so that we can see it work. What is a string that we want to check whether it is in the language or not? You can either choose something that is in the language or not in the language, and I'm not going to ask you because I don't want to know. We're going to figure it out.
Or B,
A, B, A, B, A, B. Why not? A, B, A, B, A, B. All right, since this is non-deterministic, we may have to fork this program at some point, but let's find out. Start at Q0, push an S. We're in Q1, the first thing we want to read is an A. So what are our options? There's an S on top of the stack. There are 3 productions that we could use with an A. I'm going to ignore this for now, even though we would be forking this program over to Q2. We're only going to choose to do this, and I'm only going to represent it if we're at the end of the string. But if you are asked to model this, there would be a fork going to Q2 every single time. And immediately rejecting because we're not at the end of the string.
There's only one where you have the A and the S.
Yes, so this one. So we push to the stack from right to left so that the stack reads from top to bottom. The SAA. So we are going to put on, we pop the S, we put on an A, and an S. So now we're past this A, on to the B. What can we do on a B with an S on top? Pop it. No other options aside from this that we're ignoring. So we're going to get rid of the S and move past the B onto the A. What can we do with an A on the top? So an A with an A on top. We get rid of it. Move past it. On to the B. What do we do with a B with an A on top? Anything else? Anything else we could do? Just this. So we're going to pop the A, and we're going to push a B and then an A. We move past this B onto an A. What do we do on an A with an A on top? We already figured this out. We get rid of it. There's only one option. We move past onto the B. What do we do with a B on top? Nothing. We can't do that. Since there's no legal transition to make on that, we reject. This string is not in this language.
So it must be more A's and B's. There could be one potential, but
Unless it's exactly one B, or,
because there's a lot of different patterns you could do.
Yeah.
Defining the function, this would be a little bit difficult when it's in Gribach.
I came up with this grammar off the top of my head. I don't really expect it to map to anything that is particularly meaningful.
So sometimes it just doesn't.
Yeah, sometimes it's still a language. This is a language.
String of W where, the number of A's cannot equal the number of B's. No matter what.
Is that true?
We could have reduced.
It would at least be part of it if that were true. A, X to B, A to A and or B. I think we might be able to do it. I think we can make an even number of A's and B's. One particular path through this. Very weird language though. But you can see that even if I come up with something off the top of my head, it maps to some NPDA, and we can go through that exact process of checking, is a particular string in that language or not? Even without knowing what language I created. I just created a grammar, created a state machine based on that grammar, and we can go from there. It doesn't have to have meaning that we've discovered in order to apply the algorithm.
It doesn't seem like any of these have like any overlapping, like, state you have to be in to use the transition, so
Yeah,
could you also easily make this a determinant?
this is probably already deterministic. Yeah, there is no an A on an S, a B on an S, an A on an A, an A on a B, and a B on an A. There's no, the non-determinism is here, and that you can always move, but the issue is you can't consume a character and do it. So you can teleport from here to here at any time. You just have to be at the end of the string. This is basically deterministic, except that you can't have lambda, I think, on a deterministic.
If we wanted to make it more deterministic in a sense, could we, in the SAA, add the S back onto the end and then,
And then make this transition on an S?
yeah,
Yeah, that would be equivalent.
Can you say that again?
so if we wanted to get rid of the lambda,
Yeah.
with the S. at the bottom, then. Yeah.
Make those changes.
That way we don't pop the S off.
Yeah, whenever we do that S, we're now going to push it back on. The issue is that I don't think this works in this case because of this recursion. Whenever we evaluate that S, we'd be pushing on an extra S that this only gets rid of that initial S. So if we don't have that recursion, I think that creates an issue.
Would you be allowed to just put some other symbol there?
You could. Yeah, some symbol that represents this was the initial S, which is why we use that bottom of stack character. So we could do something like, instead of pushing on this S will come on there, and we can push on a bottom of stack character that we take off here. That would work.
You could also just push the bottom of stack and S in that initial transition.
Push it on top of this, like SZ.
Yeah.
Yeah, that would work. And then you would read and pop the C when you do that. That would also work. Lots of different ways to do this. All of them are right. It just has to be logically sound. Questions on this or next questions?
I have a next question. The property number, what assumption does the pumping lemma make and why are they valid?
So the pumping lemma is going to assume that the language that we are discussing is not regular. Or sorry, it is regular. Making the assumption that it is regular leads to a proof by counterexample. Because we can derive that. We can derive the fact that it's not by that assumption. We're also assuming that the W that is picked as the string is in the language. That's an important assumption that we are making. It is necessary in order for the rest of your proof to work. If you pick a string that is not in the language, then it wouldn't have been accepted by a DFA that was produced for it. So if you iterate some more loops, you're basically stating that something that wasn't accepted iterated more loops. Well, it's not accepted, therefore it's not regular. But you can only make that claim if it was accepted in the first place. If it was accepted and you go through some loop in that DFA multiple times, then the result should also be accepted. How are we doing? What's the next question?
Can you cover some of the common pitfalls and like problems with the pumping lemma?
Yeah, common pitfalls with pumping lemma.
Yeah, I haven't, lost it.
Yeah, so important common pitfalls. The first is picking a W that's not in the language. I think that is extremely common. The place where I see that the most on the homework is in the prime example. If you want to choose something that says, pick a to the m such that m is prime, or even just pick a to the m. There is no guarantee that m is prime. If m represents the number of states in the accepting DFA, what if the number of accepting states in the DFA is not prime? That's an issue. So the way to pick something that is in the language is to say, choose the next prime that's greater than or equal to m, the number of states in the accepting DFA. We know there is always a prime number that is larger than some given number. The prime numbers don't stop. We've proven this. So you can now state that the next prime past m, have that be, define that as some other character. And then say that that's the length of the string. Remember that the string that you pick also has to be greater than or equal to the length of m. You can't say the string is a, because we need to at least get to and iterate a loop. And the longest loop that could be there consists of every state in the DFA. So make sure you're picking a good m. From there, there are lots of logical flaws that you could fall into from the actual working through that you are doing. Remember that you can pump down and not just up. So you can set I equal to 0 rather than I equal to 2, 3, 4, 5, 6, etc. Some languages will need you to be able to pump down to be able to show something. Remember that you have to make this work for every possible length of y. So we said that the length of y is between 1 and the length and m inclusive. So we need to make this work when we say that we need to be able to find a counterexample. This has to work for the length of y equals 1, the length of y equals 2, the length of y equals 3, all the way up to this arbitrary endpoint m. The number of states in the DFA that recognizes this language that doesn't exist. So it's another frequent mistake that I see is, and another one is instantiating m. If you at any point just say something like, let m equal 5. Can't do that. You have to carry m all the way through the proof. Another one that I just said in words would be something like, if the length of y is 3, then you eventually derive a counterexample. This just says that no DFA with 3 states exists that solves this. We need to be able to state that for any possible m. And any length that this says, sorry, the loop length is 3. If the loop length is 3, then there's some DFA with a loop length 1, 2, 3. Well, what if there's a self-edge? We haven't said anything about whether it's possible with a self-edge if you instantiate the length of y. So we have to prove it with a counterexample for everything between 1 and m. So that means that we need to come up with an expression that I can use the example of like the, what was it, a to the n, b to the l, a to the k, such that k is not equal to n plus l. That example, for every length of y between 1 and m, the only way to ensure that we get that is by using this factorial. M factorial can be broken down into m times m minus 1 times m minus 2. So we can always factor out anything between 1 and m that shows that this is a multiple of every possible loop length. So we can always, with some I, pump up to getting to m factorial. So that becomes what you have to use as your example, because there's no other possibility. There's no other way to guarantee that we can break the language. So as you're solving pumping lemma proofs, make sure that you are considering, I seem to have moved off the board here a little bit. Make sure that you're considering these conditions and that for every length of y, for some value of I, you have to get up to something that breaks the language. What breaks this language? K has to be equal to n plus l. You can think of this as you need to find a way to set k equal to n plus l for every length of y from 1 to m for some I. And the only way to guarantee that is if we start with a factorial. Then there will be some pump that gets us to that. Questions on any of this layout, the common mistakes that I see throughout this? Not next, yeah, question?
So I guess just the abstract, the in bird's eye, if you're pumping them, is pretty much for any combination of a loop that you can have to try to generate this infinite language, there's some I number of loops that can generate something that breaks the language.
Yes, yeah, via some number of iterations of that loop, we get to a point where whatever the restriction is, we've reached something that fails that restriction. So the failing of this restriction is that k equals n plus l. There's no greater than, there's no less than. The opposite of a not equal to is an equal to. So with some number of pumps of this, for each one of those possible loop lengths, we have to get to what breaks the language. Questions, clarifications?
In the game,
Yeah,
and your opponent is given UM,
yeah.
how are you saying m factorial then? 'Cause if he's giving you this raw number, he's not giving you the factorial of it.
Right, you would say that the string is that number factorial. They would say n is 3, you would say, all right, my string is now a to the 3, b to the 3, a to the 3 factorial plus 6. Yeah, for this problem, you needed to incorporate this because the difference between this and these had to be that factorial. The difference between k and n plus l had to be a factorial. So if you add that k plus n plus l, that gets you to what breaks it. Yeah, and to one more time talk about the game. The purpose of the game was to show that player one cannot win the game no matter what they do, not to play the game once. It's to show that in general, this game is unbeatable. You could write an AI that plays the role of player two such that player one can't win. It's like tic-tac-toe. Game cannot be won against an intelligent AI. So if you could code an AI that says you could prove that tic-tac-toe is unwinnable against an optimal opponent, it's very similar. Showing that I didn't win this time isn't the equivalent of I can't win.
The abstract is for all possible games you could play, given an optimal policy, you could not win.
Correct.
That's where we get into all the cases.
Yeah. For anyone in game dev, tying it to game dev a little bit.
Could you just talk about producing the ambiguous grammar?
Producing an ambiguous grammar, great. Or showing that a grammar is ambiguous. So first and foremost, how do we know that a grammar is ambiguous?
If you can create the same string in 2 different ways.
Yes, there exist 2 different paths through the grammar that create the same string. So applying different sequences of productions to produce the same string. So what is an example of an ambiguous grammar? What would create that?
You have 2 non-terminals that can produce the same terminal.
Okay, so we could do something like S arrow A, B. And now A can produce A and B can produce A. There's still only one path for this, but how could we turn this into something that is ambiguous?
S is A, B, or B, A.
Yeah, there we go. So now we can come up with something like S arrow A, B, which becomes, we're going to resolve the A, this becomes A capital B, and this becomes AA. It's actually ambiguous here even, because there is a path where you can take S arrow AB arrow capital A lowercase a arrow AA. So even that was ambiguous by itself. Now there are 4 ways to do it if we include BA. But if we wanted to draw this out in something like a parse tree, we would start with S. We would say this S gets broken down into an A and a B. Then we can turn this A into an A and this B into an A. If you have this, you can show that we can now have B A that produces A and A. And since these are not the same parse tree, then this is ambiguous. 2 different paths through this using different productions that end up giving you the same string.
What do you mean by produce ambiguous grammar? Like,
So if I said something like, produce this, basically I say, if a question that I could ask you, produce an ambiguous grammar and prove that it's ambiguous by drawing a parse tree.
Ambiguous grammars are something you can prove that they are, you can't say that they're not, because you can't train all the strings.
Yeah, it's really difficult. You can't show that it's ambiguous easily. Actually, we're going to get into that a little bit when we talk about LL grammars.
This is easy, sorry. You were saying that it's hard, are you saying that it's harder to prove that something is not ambiguous?
Yeah.
That's, okay.
Yeah, it's harder to prove that it's not. You have to show for every string that's in the language, there's only one path through the grammar.
So on the exam, if you ask, show that this grammar is ambiguous, that's all you need to do is just show it is.
Yeah, if I give you a grammar and say, show that this is ambiguous, parse tree will work. This will also work. If I were to say something like, give me an ambiguous grammar, construct an ambiguous grammar and show me that it's ambiguous, you could do this and then this, or this and then this. Either of those would work. And they're ambiguous because they produce exactly the same string, and following a parse tree, a depth first search order of this gives you A, and A, but the actual non-terminals that you visited in which order were different. 1 and then 2.
I was wondering, if you could show the, steps to convert this,
Yeah, steps to convert to CNF, we can do that. Anything else on this before it goes away? Right,
CNF is Chomsky.
yes, Chomsky normal form.
Can I ask a quick request? Can you have the grammar where there's like, it has 2 options to it?
Yeah, in fact, somebody give me a grammar and make sure there's at least a production with 2 options somewhere in it. And we'll convert it into CNF. So needs an S, what can S go to?
AS.
Yeah, it's
ASB, we love ASB. What else can it go to?
C, let's say that's in the language too.
So lowercase c?
Yeah.
All right. We're basically done.
Yeah.
We want to make this a little bit more complicated, I think.
Let's make
A S capital B.
This S a capital.
No, make that B capital B, and then make B evaluate to A B. Or B.
Evaluate to, sorry,
A B,
lowercase or uppercase?
uppercase,
Uppercase A, B,
or lowercase b, and then A evaluates to state.
that's already in CNF.
Now my bad.
A, B, capital C, capital A, or
Nice
C.
to look at. I don't know.
Capital, just things like that, yeah. What's capital A gonna go to?
Good question.
A, C, or D,
So capital A, capital C, or
lowercase b.
lowercase b? All right, we'll have one that's already in CNF, that works.
Then make the capital C lowercase, so we don't need to define it.
Capital.
Sure. That works. You can see how much harder it is to come up with something that's interesting, yeah. Yeah, we can have a lambda in there. Which one can go to lambda?
Let's make C, do a lambda, and do something else.
Oh yeah, we need to define capital C, don't we? Can't forget that. C can go to, not just lambda, that'd be boring.
Oh, one of the productions.
A
Let's say
lambda.
something like, let's really make it S A B A A.
S,
Let's
A,
really make this
B,
complicated.
or
All day.
lambda. I love it. This is gonna be fun. So the first thing, CNF cannot have lambda in it, so we need to get rid of lambda. How do we do that?
Make a production without the non-terminal.
Yeah,
aliases.
so look where this goes to that. And this is now going to split into 2 productions. One that makes it go away and one that keeps it. So this is going to say that this can now go to just ABA. This production without the C. And now we can get rid of this lambda. Because this C can now only go to SAB, not the lambda that it could have gone to before. This is the equivalent of back propagating that lambda up through the grammar.
You over that again, missed that, trying to copy that.
Yeah, so this had an or lambda, this wasn't there yet. So if this C can go to either one of these things, if this C goes to this, we can leave this C there. If this C goes to lambda, then there's an extra production here that just doesn't have that C in it. Those are the only 2 options that this C can produce. Something that's already there, or this production that we added without the C. Now we don't need the lambda because it's unnecessary. We covered our bases. So in general, yeah,
I was gonna say, so you fork only where this the non-terminal C is being called.
yeah, I would say look for all instances of that capital. And then wherever there's a lambda for that, you will say it can become any of those productions. So just add a production where it goes to lambda and backtrack that to where it was defined. We could have B arrow A, B, C, A. I'm not even sure this grammar fully terminates, but you get stuck in the A, B, C, A, there's no way for that to terminate. I guess no, the S can terminate, the A can terminate, the B cannot. It's always an easy fix. It doesn't have to mean anything.
Just throw an extra terminal.
There we go.
There was already lowercase c a for b, wasn't there?
Yeah, lowercase c a, but then the, I guess, yeah, the A can terminate.
Yeah, that.
Yeah, that is true. So we don't technically need this. It's just a very strange, long path. So let's get this into CNF. So first thing to recognize is we want to add productions for every terminal character. We see that A's and B's and C's are the terminals that are in this language. So I'm going to add a production, D that goes to A, E that goes to B, and F that goes directly to C. Those are the only thing those can do. You cannot reuse something like S arrow C here because S can go to this or that. If you were to make something that just said, whenever we have a C, we go to S, we'd be adding the ability for it to do this, which is not what we intend. Otherwise, it would be a capital S, not a lowercase c. So we need a non-terminal that represents every single terminal. Now we're going to go back through our initial productions, and we are going to convert all of the terminals into the associated non-terminals that we just made. So where we see an A, that's going to become a capital D. Where we see a lowercase c, it's already in CNF. We're going to leave it. We're not going to convert that into a capital. So if it's standing by itself, that's the only time you don't do this. This C becomes a capital F. This B, because it's by itself, stays by itself. This C becomes an F. Now we're going to start going through our productions that are longer than 2. So things that are not in CNF. This, and this. I'm gonna quickly, just because I'm optimizing this, if we were writing an algorithm for this, then there's the general algorithm is we're gonna take the first character and then make something for everything that is left. But I'm gonna look for the common substrings, just to save you a little bit of time on an exam if you have to do this. There's an AB here, an AB here, and an AB here. So I am going to make a production G that goes to AB. And I'm going to replace all of the ABs with G. So now this one's solved, and we still have a couple left. Doesn't really matter which ones we do here. We're going to make an H that goes to, it doesn't really matter if it's DS or SB. I'm going to make it SB. And replace this SB with H. You can either choose GC or CA. I'm going to choose CA. We're going to set I goes to CA. And this CA becomes an I. I'm going to make it an actual I so that it's distinct from the ORs that we are using. And we'll see now that everything that is left is either 2 consecutive non-terminals or a single terminal. So this is in CNF. The general algorithm, again, that is on the slides, if you're looking at the slides, if you have some production like A arrow, A, B, C, D, E, it's going to tell you that you want to take the first character and come up with a new thing representing all of this. So your F now would represent B, C, D, E. And you would replace this with an F. Recurse on this. Replace the C, D, E. With a G, recurse. But if you see, it doesn't really matter where you pull those substrings from. If you see overlaps of common characters, there will be fewer steps to this if you can group them together like we did here with the AB, finding 3 different distinct places. So if you're doing it by hand, that's faster. If you're running a program, this is consistent. Questions on conversion to CNF? So CNF is used for CYK. GNF is used for conversion between grammars and NPDAs.
Can you go over, how to identify and remove useless productions from CFG?
Yeah, so we have some context-free grammar, and we want to make sure that there aren't any useless productions. There are a couple of ways that we can have useless productions. The first one is that we just have a production that is unreachable. An example of that, anything else I can do with this before it goes away? So maybe we have something like S arrow, capital A, B, great. And this still can't terminate as itself, but you know, A, now we can make it terminate. A goes to C, and single string in the language doesn't matter. But now we have like a B arrow something. Since nowhere else in the grammar is there a capital B, this production is unreachable. So we're defining something that we can't get to. It'd be like defining a word in English that no one has ever used or thought of.
Isn't that what teenagers do?
Yes. Whatever the next generation is, they're excellent at that. I cannot wait for Skibbity to reach college.
I think that statement alone is getting there.
You're right. It has nothing to do with the fact that my sister-in-law is an elementary school therapist.
There's,
I hear it all the time.
I'm sorry. There's no amount of therapy that can get rid of that.
Once you know, you can't unknow.
You know what the most disturbing thing about Skibidi is to me? Like, the fact that not only is like, it's a thing that apparently a thing that transcends the language barrier. I remember seeing a cartoon where in Polish, some characters like, no jak tebe Skibidi Sigma. Like this.
Yeah, right. There's no translation in any other language, so you continue to hear it everywhere.
Yeah,
It's in no language, therefore is now in the universal language.
Right, there we go. We have to, a Turing machine would eventually generate it. It's in the universal language.
Can you go over the one thing where?
Yeah, yeah, throw that one up for me.
So it's S, terminal A, and then or, A, or terminal A, non-terminal A. To non-terminal B to a non-terminal C. Oh, sorry, or between each of those. So, or.
Yeah.
And then A is, terminal A, non-terminal B, or lambda. And then B, or non-terminal B is to a non-terminal A to a terminal A. And then C, or, C to a, to a terminal C to a non-terminal C to a non-terminal D. And then non-terminal D to 3 terminal Ds. Or, non-terminal C to a terminal D.
Something like this. All right, so first thing, are any of these unreachable? No, we can reach anything, which is interesting, at least for now. So that's the first thing you want to look for is every non-terminal reachable. So we can get to an A here, we can get to a B here, we can get to a C here, and we can get to S to C to D. So things are fine. We want to look for productions that cannot terminate. So anytime that we end up in an infinite loop where we can't eventually terminate. So if we get to the C, we produce a C, but then we have to recurse to a C that produces a C and recurses to a C, which produces a C and recurses to a C. So this tells us that there's no way to produce a single string that's in the language that has a C in it. I mean, imagine starting this with S arrow C arrow. You can create C, C, D, but then when you want to resolve the C, that becomes, we have the C, we get a C, C, D followed by the D. The C just becomes the C, C, D. And there's no other production here to choose from. So you have to continue to expand this. It will never all be terminals. So there exists 0 strings in the language defined by this grammar that utilizes this path. So this represents the same language as if we got rid of this production. If we get rid of this production, we also want to get rid of this because now C doesn't exist. We want to get rid of this because C doesn't exist. But now, is D reachable? D was only reachable before through C. So we're going to get rid of that because that doesn't exist. So here's the new grammar. No C's, no D's. And it represents the same language because for every string that exists in the language, it could have been produced with these 3 productions.
You replace the non-terminal terminal A for the B production into S.
Into this.
Yeah.
Intriguing, the non-terminal A going to an S.
Yeah, just putting that directly into S.
Yeah, because it can either be, the issue is the ordering of these. Because S can go back to this, which produces another one, but then it only ever produces just that one. So if we made an S, we could go back and forth and produce an arbitrary number of A's. So I don't think we can, but it's a good idea. There are lots of tricks to simplifying context-free grammars, and there are just so many of them that you kind of just have to use your intuition to figure out, can we eliminate something in this or make it simpler?
The main question was, is that we can eliminate D, but then we lose the capabilities to generate more Ds. Is that okay, given an?
Well, what went to the D? It was just in the middle of this. So we could evaluate these Ds to make more Ds, but we still could never resolve this C. And the only way for the D to get there is through a C, which we had to evaluate.
Because the D could also terminate on 3 Ds as well.
Right, but the only way to get through that D is to have a C somewhere in your string. Which means you have to evaluate that C, which will never terminate. So give me an example. If we go back to the old, crap, I'm gonna forget what this was. C went to, I remember D, that went to D, 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 or C, capital C, lowercase d. And what was C again? C did
Lowercase c, uppercase C, D.
uppercase C, uppercase D. Yeah. So give me a string that has 3 lowercase d's that's in this language. And I will argue you can't do it. Yeah, because the C can't be evaluated. And we have to go through this C to produce this D.
Because we can't terminate if we go that
Right.
route. It's
So we
not
could
that.
terminate directly from a D, but there's still this infinite recursion in this C. So we can evaluate this, we just can never evaluate that. That's the lowercase c.
They look back and forth between each other, so it's not possible.
Right. Right.
This language, just A star.
Probably. Didn't take the time to think about what the language is, but oftentimes when there's some kind of learning outcome to this, they'll make something that's really complicated to represent something that you could have represented significantly simpler.
I mean, it's the same with the one we generated for a random example for CNF conversion.
Yeah.
It's just something that was as gross as we could imagine,
Yeah.
and then try to rehash it.
It's funny from a student's perspective, but think of being a textbook author. You're tasked now with coming up with an example grammar that has both an unreachable, making it as difficult as possible to get to an unreachable production. And also, so it doesn't look like there's an unreachable production when you first look at it, but there becomes one when there is recursion. Generate that example, but also make the language meaningful. That's a much harder problem. It's a lot easier if you're trying to teach someone how to remove useless productions to not really worry about the language that's there. Because the purpose of this is not to represent an interesting language, it's to show, here are the two main ways that you can get to useless productions.
And funny answer to the question. We got the little side plus where you simplify it all the way down.
Yeah. S arrow, A capital A capital A to A capital A or A. Done. All right, we are out of time, but I do have office hours for the next hour. If anyone has any other questions, I'll throw this video up in case you'd like to look back over anything that we did. And we will meet tomorrow for everyone's favorite activity.
We're allowed like.
Yes. Full sheet of notes, front and back.
Oh, wait, you probably posted somewhere on. Right?
Yes, it's in the study guide for everything that would be on the exam. All of the slide decks for that are also posted, so you can look back over all of the slides. Anything on the study guide, let me know if you have any questions on that. I'll get to it when I can.
So that's a question for.
Yeah.
Are we doing that? 10, 11?
I have to look at exactly what was covered.
Because it didn't tell like the exact slide number.
Yeah.
Because I just wanna like, oh yeah, these are all.